Okay, I think we could get started now. So today we have Maximilian from TUM to talk about the energy-based coarse-graining. Okay, I will give it to you. Thanks.
All right, can I just share now?
Yeah, sure.
Share. Can you see my screen?
Yep.
Second. Okay, all right, it works. So should I just start?
Yes, please.
All right, then thank you for the invitation to be able to present here. My name is Maximilian and I'm from TUM from Munich. And I will be presenting my current or our latest paper about energy-based coarse-graining molecular dynamics. And if you have not seen it yet, you can take a quick scan to go to the archive preprint. And I will start today with going over the contents and then with a small motivation about the topic for anyone who is not familiar with what the paper is about. Some small problem definition. I will introduce our flow-based framework and give you some model specification and go through the results. And then at the end, just a quick outlook what's next. And I imagine at the end we have a question session where we can talk about any details. I assume it's planned that you do the questions at the end, or do you want to do it during the presentation?
I think it's up to you. It's up to you.
Okay, yeah, for me, we can do it at the end. Just remember the
Yeah,
slide
for
and we
sure.
can go back.
Yeah.
All right, then I will start. So the paper name is Energy-Based Coarse-Graining. And the three big points which you have to know about to understand what's going on is, first of all, what is energy-based, what is coarse-graining, what's molecular dynamics. I will start with the last one, which is molecular dynamics. So what is MD? MD is a way to explore spatial and temporal limits in around the nanometer and microsecond scale. And it's usually for a lot of interested biophysical processes quite impractical, because a lot of interesting stuff is happening at much larger time and length scales. So MD is a way to get to the problem, but most of the time we are out of the interesting scales for interesting problems. And this is where the second part, the coarse-graining part, comes in. So this is already probably a lot of you are familiar with this, a very old concept where you do some coarse-graining in order to increase the spatial temporal limit of MD. And what we're gonna do in this paper, we do something similar to bottom-up coarse-graining methods. So in general, what is coarse-graining? You have some all-atomistic, all-atom model, and you find some kind of mapping between a coarser grain scale, where you define some kind of pseudo-atoms, for example, which has less accuracy, but is mostly much more computationally efficient to simulate in most cases. Obviously, you have some drawbacks. You have some kind of loss of information, especially when you want to go back from your coarse grain scale to your fine grain scale. Yeah, and there are a lot of different methods how to do coarse graining. There are bottom-up methods, top-down methods. In this paper, we're mainly looking at bottom-up methods, which means there is already a coarse grain model available for the high-resolution one. And through first principles, you try to find an approximation for the coarse grain model to represent your all-atom fine grain model. And how does it look in practice? In practice, it could look something like this. You have some bioprotein, for example, here, and you could try to find one coarse grain mapping from this all-atom picture to the bottom coarse graining model. There you have to define this mapping operator R here, which is important. And I will introduce now a few of these methodology, which we need later on. Our X in this paper is always the atomistic coordinates. So our all-atom picture and our Zs are mostly our reduced coordinates. You can think about the coarse grain coordinates. We use it a little bit different in our model, but it's very similar. And what we want to do, we want to calculate some physical observables on our all-atom model. But usually what we have to do, we have to solve this expectation here, we have to solve this integral, and we don't have this target density available, this Boltzmann density. Normally you do some MD, you generate some data, you can approximate this, or in the coarse-grained analog, you generate some coarse-grained simulation, and hopefully this is close enough to the all-atom picture. So this is the general idea between MD and coarse-grain, which is important for this paper. Just a quick overview. And what you normally do in this case, for the coarse-graining, you have this two-step procedure, which means you have to first generate some MD data, and then you try to learn approximation for this target Boltzmann distribution, which means this is one of the problems with, in general, database approaches, for example, database coarse-graining approaches, which is this chicken and egg problem, which means you need MD data in the first place to train something to replace the MD data. So even if you want to learn some coarse-grain potential, which you could substitute your all-atom force field, you would first need to generate enough all-atom data in order to learn your coarse-grain potential. So everything which was not included in your all-atom data will also be missed by your coarse-grain potential. So this is kind of a drawback, and this is where the third part of our title comes in, which means energy-based. And I will later show you how we try to use the potential energy directly, and we will not rely on any training data beforehand in order to learn our model. So for our framework, this might be now a lot of information, like a lot of this, especially the right side, will be more clear later on. But the general idea is we have some kind of normalizing flow where we try to approximate some lower reduced model. In this case, remember the Z, you can think about something like your coarse-grain variables. And then we have a conditional distribution going from the Z back to the other coordinates, which are missing, which you leave out, which you coarse-grain out of your all-atom picture in order to reconstruct the full atomistic picture. So this is kind of the idea. You have some normalizing flow which works on a lower dimensional representation, and the idea is that these Zs, your important degrees of freedom, include all of the necessary information, and then you have some conditional distribution which brings you back to the all-atom picture. And you learn all of this through energy training. And yeah, this is kind of the overview, and what can we do later on with this model? Later on, we have a model to approximate the all-atom picture, going from your flow model back to this conditional. So you will not end up with a coarse-grain model, which lives in your coarse-grain space, but you will have, at the end, all atomistic coordinates recovered. So we will learn some kind of transformation from both of these maps to the all-atom picture. And we do all of this training based on energy training, which means we will only need to evaluate the potential energy, will not need any data. And I will go in some of the problems which comes with energy training. A lot of people also try this as well, and they have different approaches on how to make this work, or why not everyone is using this in this way. So yeah, at the end, we can then just generate unbiased one-shot samples. We don't need to simulate like with MD or MCMC, but we can just query our model. So this is the general idea, and now I will go through the methods step by step. What do these parts on the right side mean? Like, what are we looking at? So first of all, I said we start with the all-atom picture, which means you can think about this are the coordinates of your molecule, of your all-atom molecule coordinates. And these coordinates, the distribution of these coordinates is approximately this unnormalized Boltzmann distribution here. Obviously, you have some normalization constant here, which we leave out in this case. And the key part of our framework is this bijective transformation, which means we have a transformation which takes some coordinate Z, some coordinates, we call this here big X, and reconstruct the all-atom picture. So what are these Zs and what are these X's? I said the Zs is some lower dimensional representation. You can think about it. It's similar to the coarse-grain coordinates, but in this case, these are not pseudo-atoms. In this case, you can think about we take the slow degrees of freedom of our system. So for example, for this alanine molecule, usually the important degrees of freedom are the backbone atoms, which kind of dominate most of the configurations. And then you have the side chain atoms, which are usually not so important for knowing how these conformations look like. And this will be we call this fast degrees of freedom. And one assumption we make here is that given your Z, so given you know the positions of these backbone atoms, to find these other axes, the other position of the side chain atom is rather easy and is quite unimodal. So this conditional distribution is unimodal given the position of your backbone atoms. So the idea is that you find some partition, or you learn some, or you find some this transformation, or you learn this transformation F, which splits your all atomistic picture into like fast and slow degrees of freedom. So this is kind of the key idea. And this fast degrees of freedom will be easy to find given you have found the Zs. So this transformation is bijective, which means it's reversible. So going from Z to X, you can go back to the all atomistic picture and vice versa. It's not a dimensional reduction. So we don't only learn some lower dimensional Z space like in Coarse-Graining, but we learn both of them, the X and the Zs, which complete the dimension of your all atom picture. And what we can do now, we can rewrite our Boltzmann distribution given this transformation. So instead of everything with respect to our all atom coordinates, we have with respect to these two transformed coordinates, the slow degrees of freedom Z and the fast degrees of freedom X. And this is just the transformation. So at the end, you have a transformed Boltzmann distribution. And what we try to do is we try to approximate this new joint distribution from X and Z with our model. This Q of theta here is a model which we learn these theta parameters from, and this joint distribution can be divided into this marginal Z and this conditional X given Z. So this is the main theme. We have this transformation which can be learned, which can be chosen at the start, and given that we rewrite our problem in terms of this X and this Zs. And one nice feature now is that because we said that these okay, maybe one thing first is we consider in this examples now a special case where we do not learn this transformation F, which can be learned in theory, but we pre-partition our coordinates, which means we determine what information is in Z and what information is in X. So similar like how you would in Coarse-Graining decide on your coarse-grain map, which you need to go from your all atom picture to your coarse-grain variables. In this case, you decide on the partitioning which information belongs in Z and which information belongs in X. Given you make a good job of this partitioning, your training will be easier or will be more difficult, or might even be not possible if you make a bad choice. But it's the same with Coarse-Grain. If you choose a Coarse-Grain map which is nonsensical, you will have a hard time finding a good approximation. And this permutation matrix has some nice features. It's the Jacobian-1, which makes some of our gradients and loss terms easier to calculate. And this is where you can put your physical intuition, your physical knowledge of the problem into effect. Obviously, for the general case, you would try to learn this bijective map, which then decides how to split into this X and this Z. Please let me know if I go too fast. And now one of the nice features I wanted to mention earlier is because we divide our all atom pictures in fast degrees of freedom, slow degrees of freedom, what we say is that given we know our Zs, getting towards our X will be quite easy. And this conditional distribution is not only easy to explore, it's also unimodal, which means that given the Z, you know exactly where your X lies. And this is one example, which is straightforward to illustrate on. This is a double well. So we use a double well potential and we try to find the positions inside this double well. And you can see these two wells here, they are different in this Z coordinate, but they are not, you cannot differentiate between them in the X coordinate, which means that if you know your Zs, so if you know the position of these wells, it will be easy to explore the X direction here, which is this vertical direction, because you don't have to make the jumps. And this is the important feature is that all of the multimodality is captured by the Z. So the Z space will determine all your minimas in your energy surface. And the axis will then just need to explore around this minima and the correct shape of your mode. And this exploration of this conditional can be done by MCMC-MD with very few steps. So just a few steps is enough to, if you already know the location here, to find the correct X coordinates. So this is the key idea. You use your flow model to differentiate the modes, and then you use to query this conditional in order to find the correct shape. And some note which we need later on. So this marginal distribution here is the let's say the target margin with respect to z, which means this governs how this position of the modes is in this case. And this we cannot evaluate. It's similar to the Boltzmann distribution. We cannot solve this integral, but we can find the gradients of the log of this marginal by this expectation with regards to the potential. And this will be a key later on when we try to find gradients in order to update the parameters of our model. So to give maybe a small summary of what the idea is now. So we want to approximate the target density of x and z, and this is divided into a conditional distribution and a marginal distribution. And we say there is some marginal distribution with regards to our z parameters, which is the unknown. It's multimodal. It's the one which decides how to differentiate between our configurations. And we have some conditional distribution, which is easy to explore and unimodal given we know our z positions. And then we try to find an approximation. We try to learn this flow model Q theta, because remember the title was a flow-based framework. So we use a normalizing flow in order to approximate this marginal, and we use this exact condition in order to get the joint distribution. And then we can build an objective function, which will be the reverse scale divergence, and we try to minimize the scale divergence in order to minimize the difference between these two distributions. So this is the loss function which we'll use to train our parameters theta in this case. And our objective, which is the scale diversion, you can write out the terms, and at the end you have two terms which are left over, which is one, this number 2 here, which is the entropy of your parameterized model, in this case our flow model, which you can easily get. And the second is the log probability of your marginal distribution, and this is unavailable. But we can do a small trick, which means we don't know how this log marginal looks like, but what we can do is we can express the gradients with this regard, with the note I had earlier. So we have some requirements on Q of Z. Q needs to be able to capture the multimodality. We said we separate our all-atom picture in some multimodal part and some unimodal part. And then also we need to evaluate this log of this target marginal. So the P's are our targets, the Q's are our approximate densities. And for this we use, like I said, a normalizing flow. We can do some reparameterization in order to rewrite this expectation with regards to Z in order to evaluate our gradients. So our normalizing flow is nothing else than a bijective transformation from a standard normal distribution. I think most people are familiar with this. And then what we can do some change of variables. And at the end, we are able to evaluate these gradients. So the key part here is that we don't know the log probability, but we know the gradient with regards to Z of this log probability. And then we can, through some formulation, we can calculate this gradient here, which is an expectation with regards to X and Z. And we are able to sample from this conditional by, like I said, because it's unimodal, you can just run a few steps of MD and already get quite good samples of this conditional distribution, and then use these samples to evaluate the derivative of the potential, which is nothing else than the forces. So this derivative of the potential is the forces with regards to Z. So you can think about, you generate your flow samples, then you run a small simulation of the fast degrees of freedom, and then you get some samples of the joint, and then you evaluate your forces at each of these steps you took. And then you just calculate here this expectation, which is nothing else than an average. So I already explained it, but I have it here again. So what you do is you draw some samples from your standard normal, you transform it through your flow model, and then you initialize some short MD or MCMC, whatever you want. And because this conditional is unimodal, it's very easy to explore compared to the whole Boltzmann distribution, which you need millions of steps in order to do the jump between different energy minima. And you collect all of the forces at each of these steps and you use these forces to calculate this expectation. And at the very end, this expectation here is nothing else than an average force. So you see kind of the response of your simulated axis on the z's you sampled from your normalizing flow. And in this case, we never need to simulate beforehand. The only thing we need to do is we need to evaluate the potential energy. And in this case, run the small MD only on some unimodel. So you don't need for your MD to ever cross any energy barriers, never to do any transitions. So the idea is that this should be very easy to do, compared to if you would do, for example, MD or MCMC on the whole Boltzmann distribution. There you need to rely on your MD to jump between all of the different configurations, which might need millions of steps to do so. Then some model details. I mentioned that we use a flow model. We use neural spline flows, which is just coupling flows, very similar to real NVP, but as a transformation, they use these rational quadratic splines. If you're familiar with this is just a bit more expressive than the normal affine layers you have in the coupling flows. We use very lightweight neural networks because the idea is that because we separate to this X and Z into the Z's and the X, that our network can live in much lower dimension and also need much fewer parameters. And then we need something to perform molecular dynamics, for example, which means we need some all-atom simulator to calculate the forces, which can be any force field or potential energy you have implemented, you've defined for your problem, and you need to query this then at all of your positions during the training. And the second part, what we need is what we employ is called temperate learning. Probably most of you know that if you normally imply some energy-based training, it's usually quite difficult because this KL diversion has some unfortunate properties, which means it's very mode focusing, which means that if you try to approximate some multimodal distribution, what usually the KL diversion is doing, it's just finding one of the modes and focus all the probability mass in there. So it rather doesn't have any areas where it's not overlapping with your target instead of covering the whole area. And what we do is tempered learnings, similar to like sequential Monte Carlo or something, is we initialize at a very high temperature. In this case, we call this temperature, it's the inverse temperature is beta, which means a high temperature would be low beta. But we initialize at a very high temperature, and a very high temperature, this potential energy surface is very flat. It's very uniform, so there's not much difference between the modes. And then you can do your training. It will be very easy to find something to resemble this surface. And then if you linearly increase the betas, each new temperature will be only slightly different from the temperature beforehand. And this allows your algorithm to slowly adjust to all of the different configurations and actually enables energy training on the cost of needing to train at a lot of different temperatures. On the bright side, you also get a solution at each different temperature. So if you're not interested at only your target temperature, but also other temperatures, you already have a trained model for each temperature between your starting and your endpoint. And I will also illustrate this at some of the examples to see what's going on and how this is working. I think which is already the next part. Okay, here's again some of the pseudocode. This is, you can look at it later in details. I think the most important part is that how our training works is we have two loops. We have an outer loop, which goes over all the temperatures, so from the starting temperature to the target temperatures, and then some inner loop, which is just optimizing the parameters. So you start at one temperature, you train your model, then you go to the next temperature. The difference between the parameters should only be slightly. So then you train again, you go to the next temperature, you train again, you go to the next temperature until you're at the target. And if you do small enough steps, the difference between each step is very slight, which means the parameters don't have to change much, which means you can do very little steps in order to converge. And I will just start with one of the examples. I think it's easiest to see for yourself, and then we can discuss all the questions at the end. This is a very easy double I showed you earlier on. How this is constructed, it's bimodal in this x1 direction and like harmonic in this x2 direction, which means what we're gonna do is we're trying to approximate this x1 direction with our z's, and this x2 directions with our big X. So this would be our slow degrees of freedom. They have to determine between one mode and the other. And our x's just have to get the shape of this mode correctly. And if you do normal MCMC, or even if you want to do a particle and then you do some MD with this double wave potential, it takes a lot of steps to do this transition from one to the other. Like this one mode is less than 1% likely than the first one. So it's a very high energy barrier between them. And this is the form of the potential we'll be choosing. Can choose also different values, then the probability of this mode might change a bit. And what we get at the end we get this right side is our prediction, something which looks very close, very similar. So this our model is able to find both of these modes. And now the more interesting part is what is actually happening during training. How is our model doing this? For this, I have plotted the potential energy on the left side. So this would be the double wave potential at different temperatures. And this is the samples from the marginals, so from this x1 direction. And we can see that at very low temperatures, this marginal distribution is very flat. So there's not much difference between the two modes, which should be around 2.5 on both sides. And also this potential is very flat. So it's very easy to learn this at this lower temperature. It doesn't take much effort, and you don't have any problems of this mode focusing because there are not so many distinct modes. And then you increase the temperature slightly and these modes get more and more pronounced. And if your model actually captured them at this temperature, it's not very likely to lose them later on. So you can just go and go until you're at the target temperature. And then at the target temperature, you see that the difference between this mode, the samples in this one and this one is like over 1,000 times more likely, which means that taking 10,000 samples, you would have like 10 or 20 here, and the rest will be in the other side. So if you would do some normal MD, you start on one side, it's very hard to cross over this energy barrier. And because we do this tempering, we actually can do some energy training without being exposed to too much of this property of the KL divergence. Yeah, this was one example to show you how this tempering works. And then we have some second example, which is a Gaussian mixture model, which is by construction, we have our Z space be our Gaussian mixture model, which means we have different modes. In this case, we have 3 modes, and we show it once in lower dimension, which is dimension of 4, and higher dimension of 20. And our conditional distribution, so our axis is just the Gaussian distribution. And what we can do then, we can do the same. We can try to learn with the flow model, this Gaussian mixture model, and also, find 3 modes in this example, or even in the 10-dimensional case. I mean, for 10 dimensions, it's hard to visualize, but if I just plot a few of these, also in like 20 dimensions, so even higher. And then if you would, for example, do the same without any tempering, just to get a comparison, what normally happens, you learn a model which is only ever able to find one of these modes. So it's very easy to diverge, and it's very easy to lose these modes if you don't do the tempering. And then, I mean, these are the samples again, like before and histogram compared to the target and the prediction. And these are some of the 20 or 10 dimensions in this case of our Z vector. And in the background, this is like the contour lines of the block PDF of this Gaussian mixture model. So these are the energy minima states you can think about. And the rest is the potential energy. So these were just some toy examples to illustrate how the model works. And now we go to one of the molecular examples, which is our target molecule in this case, which is coarse-grained alanine dipeptide. It's just, you could also do normal alanine dipeptide. In this case, we do it with coarse-grained alanine dipeptide, which has this hydrogen atoms removed as our target. And we do this pre-partitioning, similar to what I showed before. We use the Z to be our backbone structure and the X's to be our side chain atoms. So this is what you have to decide beforehand. You have to decide how to do this pre-partitioning. This is at the moment one requirement. I'll go in the Outlook then how you can substitute this, but this is what you have to use the physical knowledge you have in order to determine what is your slow and what your fast degrees of freedom, or where could they be. You could even use more Zs than necessary, but it's important that you don't miss out on any. And then this is the target distribution. In this case, this is the Ramachandran plot for the dihedral angles. This potential we chosen here also includes all of the mirror images in this case. It's from a graph neural network called DimeNet. And yeah, this is a very multimodal distribution which has like multiple different minimas. And our target temperature is around beta target around 0.4, which equates to 300 Kelvin. And this is what we're going to use as a target to train our model. You can see at the start, it's very nice to look at the Ramachandran plot because it shows you all energy minima states, kind of, or like the most important configurations. Like here you can see this C5 and C7 region. These are the kind of the regions where you can normally find in this molecule in alanine dipeptide. And at, for example, our starting temperature, this space just looks completely flat, which means that at the lowest temperature, there are no distinct angles. Our molecule is at thousands of degrees of Kelvin, which means it's not even, it's just a gas or like a liquid, so that there do not exist any special features in the Ramachandran plot. But as the temperature increases, you can see there will be areas forming which are more likely to be included, and the potential energy impact gets more and more, scaling with the temperature. And at the end, this is what one of the results look like, which means you see this minima are the different main points of the dihedral angles this molecule has. And usually if you find these, knowing the dihedral angles, you can determine most of the configurations of this molecule. Yes, this is one example. And do you want to say something? Sorry. Oh, yeah, and this is for the target temperature. Yeah, and this the angles in decrease in this case. And this was already it for the results. I will now do a small conclusion to sum up what we are talking about, and then give you some outlooks on some things we're currently working on, which might even be included in the journal paper in the end, which is going to be out hopefully like in a few weeks. So what we did, we combined the all-atom simulation with coarse-graining and energy training. We rely on some physical insight, which means some decomposition of our X into slow and fast degrees of freedom. And our assumption is that given the slow degrees of freedom, our fast degrees are unimodal. And this process allows us to be fully reversible, so we don't have some loss of information with coarse-graining. We can always go back and forth between our Z and X's. And the marginal distribution inherits, in our case, all of the multimodality. And our normalizing flow is used to approximate this marginal distribution. And then we get some trainable model, which doesn't need any all-atom simulation data and can generate unbiased and one-shot equilibrium samples. And then some of the outlooks, some stuff we're currently working on. So currently this transformation in this example I showed you is determined a priori, but you could also learn it, which means this transformation, you only would need to decide the dimension of your fast degrees and slow degrees, but which actual positions of your Z corresponds to your X can be learned. This is something we're looking forward to do in the future. Also, you can, instead of what we're doing right now, where we query this conditional with very few samples, you could also get rid of this and just learn a model to cover this trainable conditional, because in theory it's unimodal. Any Gaussian distribution might be a good fit. Also, I mean, there are some other improvements for the future, like the Cal diversions and this mode-seeking behavior, which we try to subdue by tempering, but then again, this just increases training time, because you don't only have to train at the target temperature, you have to train at each subsequent temperature. And if you're not interested in them, you kind of train for a lot of steps which you're not really interested in. And there are some other divergences you can do, like there are some divergences which have more like mask covering properties, which might be more relevant or might be more suitable. And also, at the moment, we employ some very, very simple normalizing flows, like I said beforehand, with not many parameters. Like our model for alanine has around 80,000, 90,000 parameters, which is in this case very little. Like most models for these cases have millions of parameters. So there can be improvements also made by employing some more powerful tools, like current continuous normalizing flows, or even diffusion models, because you just need anything which is very powerful to predict the multimodal distribution in our set space. And this is it. Thank you very much. I hope I wasn't too fast in talking. And yeah, open for any questions you have. Yeah, so just.
Hi.
Thank you. So, do anybody have any questions? Feel free to ask.
Yes, I will have a question. I don't know if you can hear me
Yes.
correctly.
Yes, we can hear you, Louis. Go on.
So I think there's something I didn't understand very
Mhm.
well. Is how exactly do you design the distribution of x given z? So let's
Mhm.
say that you have your peptide. So z is some atoms, x is some other atoms. So given a z,
Yes. Let
how
me
do you
go
define the density of x given z?
1 second. Let me go here. I think it's here. So you're asking about this, right? This x given z.
Okay, so you use base. Okay.
Yeah, so the idea is, in theory, this conditional distribution, like you said, it's just a base formula from the marginal and the joint. And what we do in this case is we try to find samples from this by doing some small MCMC. So we define it, like you said, from base, but you don't need this marginal. The nice thing is if you do MCMC, you just need the unnormalized density, which means you just query the target density given your set samples from the flow. You simulate for like 10 to 100 steps, something very small, and then you get samples of X given all of your Z samples. And you can also do this in parallel. So you need to just evaluate the potential energy function. Like
All
for
right.
the future, what we're trying right now is to just, because we assume this is unimodal or very easy to determine given your Z, right? Because in theory, all the multimodality is in Z. You can approximate this distribution by, for example, a Gaussian with some learnable mean and standard deviation. And then you can train your Gaussian with your other network in tandem, and you don't need to do this extra MCMC, even though we found out you don't need so many steps, but still, like in all of these examples, evaluate the potential energy is always the most costly factor, right?
All right, super clear. Thank you very much. And I had another question. So
Yes, please.
during training, you will evaluate the gradient of this U50 function,
Mm-hmm.
which is involved in the loss. How
Yeah.
many times do you evaluate it? And what if you do an MD simulation with exactly the same number? Like, do you actually evaluate the forces less than when doing a very, very long MD simulation?
Yeah, this is a very good question. I actually don't know the exact number. But this is a very good question. Yeah, because if you, for example, would evaluate this as often as you would do for the simulating it anyway, right? There's not much gain in computation.
Exactly.
I actually don't know by heart the comparison, but it all depends on this tempering. So if you just train it for each target temperature, you have very little steps you need to take. Like you need to take, like I said, around 10 or 100 steps. But if you do 1,000 tempering step, that scales already quite a lot, which is like 100 times 1,000, right? And I think in the paper we did around 500, 600 steps. But then again, our MD simulation is around 10 to the 7 or something steps. So this is still much more steps than even if you calculate all of the MD and all of the tempering. But yeah, it's a good question. It's probably also good to include a comparison in
Mm,
the cost versus the reference simulation. But yeah, I would assume it is still much less because this
yeah.
takes a very long time to do to get to this reference simulation with this reference plot. Here, where is it? Yeah, to get this, you need still very, very a lot of steps, yeah, to get this.
And I had one last question,
Yes, please.
if no one else wants to ask something.
Go for it.
So, can you compute free energy differences between two modes using this technique?
Yes, you can do it in the Z space. Yeah.
Okay, in the Z
can do
space,
this.
but not in the full space in the end.
Yes, you would have to try to recover it then through this bijection. But yes, what you normally do, you would do this in the Z space, but the Z space has in theory the same modes as your all atom picture. And this is, for example, one of the improvements we are doing at the moment, or we're trying to do, which is to if you learn this, where is this? Do you have it in Outlook? Yeah, if you learn this condition as well, you actually get access also to the target joint distribution, which means you actually get to calculate this free energy difference also in the atomistic space. So this is something we try right now, where you don't need to query this conditional, but you just learn it. Because if it's unimodal, it should be easy to learn as well. And then this allows you to get the target joint. Then you can do some improvements, like you can actually calculate the exact KL divergence as well, and you can develop some adaptive tempering schemes as well. You can calculate this free energy difference in the atomistic space, not only in the Z space. So this is there's a lot of advantages which goes together, but yeah, something we're actually doing right now or trying right now.
All right, thank you very much.
Okay. I have one question.
Yes, please.
So, just to clarify first, so after your model is trained, during your sampling, are you first sample a set from your normalizing flow, and then you run a short MCMC to get the capital X given this set?
Exactly. Currently, it works like this. Yeah, you
Yeah.
run a Z.
So in this case, you cannot calculate the density of your proposal, right? So because your proposal is get by first sampling from normalizing flow, the density here is none. However, when running with the MCMC, the proposal density is unknown. So I mean, in this case, when you are doing your exact sampling, you are not going to reweight your sample at the end, right? You're just sampling a set, run MCMC, and get a joint without reweighting them.
Exactly, yeah, because you don't have access to the complete distribution.
I see. Yeah, I'm thinking maybe in this way, normalizing flow can be somehow harmful to the model capacity, because I think normalizing flow is not usually a good generative model unless you need the model density. And because during the training you're using the gradient, and with the reparameterization trick, you don't need the model density as well. You only need this gradient. So I'm thinking maybe I don't know, but maybe I think doing something like uh implicit sampler instead of the normalizing flow can be also a good trick.
Yeah, for sure. I think this model, I mean, to be honest, it's just a model we're using, this normalizing flows. There's a lot of room for improvement to do something better there, because you can also see that it is very light. I mean, one of the advantages is very lightweight, but we also see that some of the accuracy, especially here, is also not super perfect. So one area we're looking into actually improve the model, or the model we're using. But yeah, it's for sure a good point that maybe this is not the best way, and maybe we don't even need normalizing flows in this case. I mean, it's just for us, because we're not really interested in like the best model architecture. It's just a model which can approximate something unimodal and multimodal, right? But yeah, it's for sure, it's a very good point. Yeah, I think there's a lot of room to improvement to do something more sophisticated here with the model, or something more appropriate even, than just the normalizing flow. In theory, it can be anything which is able to approximate our Zs.
Yeah, I also have one. Yeah, go ahead.
Sorry. Sorry. Maybe just a quick question. So, so how should we choose the variable Z and the capital X, the slow and fast modes? For example, for molecules, because I'm not very familiar with physics and chemistry, in like is splitting like this as the backbones and the residuals is like is a universal way to do this, or?
Yeah, this is currently, I mean, where you have to use your physical or like chemistry knowledge. In this formulation, what you have to do, you would kind of have to know, okay, probably these atoms are more likely to be responsible for the slow degrees of freedom, and these are maybe not so important. What you can do, obviously, you can choose your dimensional set to be higher than necessary. Because for our model, it's only necessary that you include them, but the higher you choose them, the bigger your network becomes, the harder it is to learn, obviously. But for now, you need physical intuition. There's one extension, which we're also trying right now, is to learn this map. And then the only thing you need is to know the dimension. So you say, okay, I allocate dimension of, for example, 10 here for Z and 15 for X, and hope our model finds the correct way. There's a few pitfalls with this as well, because it's very easy for the model to get some degenerate solutions, but this is some stuff we're trying right now. But for now, this is where you have to actually use your a priori knowledge. There's not a good way to do this other than, yeah, at the end have it learnable and not predetermined.
I see. Thanks.
Yeah, I can continue. So for
Yes,
the
please.
potential energy function, you use this like coarse-grained potential energy, right? It's not an
Yeah.
atomistic one. So assume that you have samples for anionic peptide for coarse-grained. Then you can train the Boltzmann emulators in the beginning to just learn the flow to generate samples. Then if you have this potential mean force as your energy function, can you just reweight your distribution to ensure it's unbiased? Because you already have like approximated potential mean force. What prevents people from doing like coarse-grained Boltzmann generators?
So can you say the first part again? You start with what?
So you just train the flow model for your coarse-grained Boltzmann distribution, right?
Like we
But
do
it's
you mean our flow model here, our
yeah,
CubeSat?
yeah. And then but with data. Then you want
okay.
with data, then it will be biased, right? Because you need to reweight your bias distribution with the energy function, right? So can you do that?
In our model, you mean? Or in general?
In general, just like a coarse-grained Boltzmann generator.
So what you want to do, you want to do a coarse-grained Boltzmann generator where you train on coarse-grained data and then reweight with the coarse-grained potential.
Yes.
And then do you want it to be approximating the all atom picture as well, or just approximating the
No,
coarse-grained?
just coarse-grained, right? Because if you only learn the Boltzmann emulator is biased, right? We want it to be unbiased, so we need a reweighting procedure that we need to calculate the density and also energy query, right? But since you have this potential mean force, like you train with relative entropy or whatever, in principle you can do that, right?
In principle, you should be able to do it, yeah.
Yeah. I'm curious if you have tried this or not, because to me it's a very straightforward idea.
Yeah, I think in principle this should work. No, I have not tried this. I mean, we're using here a coarse-grained potential. Any target could work for us as well. We're not using coarse-grained because we want to do this with coarse-grained necessarily. Yeah, but I don't see why it should not work, because you're not targeting like the full atom picture afterwards, right? You're just interested in finding an approximation for the coarse-grained potential. And this should work at your target temperature, right?
Yes. Yeah. Okay.
I think
Yeah,
so.
we can give a try later. Yeah. Because a lot of people just for Boltzmann generator, people just focus on atomistic system, right?
Yes, that's true.
Yeah, it'd be nice that you can have like a coarse-grained Boltzmann generator, I think. But there's something missing, but I'm not sure.
Yeah, no, very, very interesting, yeah.
Yeah. Okay, and also for the architecture, I think for Boltzmann generator, there's this recent like a sequential Boltzmann generator paper that you can use this tar flow that to scale Boltzmann generator towards like 3 peptides or even larger system. I think you can give it a try. It's a still flow model.
Yes, I remember the paper. Yeah, also, I mean, for this case, alanine is a rather simple molecule, right? In
Yeah,
theory, the idea would be to scale this up as well. I think, in my opinion, we probably have to first make these improvements, maybe learn this conditional, not use it, because then it gets very expensive if you have to evaluate the potential, even for like a few steps during tempering. This scales up very fast, very easily. But yeah, there's still a lot of room for stuff to try out.
Yeah, that's why I said that maybe we should not only focus on energy-based training, right? If we have samples for coarse-grained systems, why don't we just learn a coarse-grained Boltzmann generator and let's give it a try?
Yeah, just for sure. I
Yeah.
mean, it's solving a different problem, but
yeah,
I don't see many people try this.
yeah. Okay, thanks.
Thank you for the questions. Very interesting.
Yeah. Okay. I think, yeah, should we call the